All right, guys. So we are starting lesson 1.11, which is equivalent representations of polynomial and rational expressions. So in this lesson, our goal will be to fine-tune the techniques for analyzing the graph of a rational function. We can use factoring techniques to write equivalent representations of polynomial or rational functions to provide information about zeros, domain, and other important characteristics. Let's establish a procedure we have been developing in our previous lessons of this unit. So example 1 says write an equivalent representation of a polynomial function to analyze the function. Use your findings to sketch the function. So in order to do this, I want to find the zeros of my polynomial and their multiplicities so then I can get a good picture of my graph. So I'm going to start factoring this by taking out a GCF of x. So I get x squared minus 2x minus 15. And then I'm now going to factor the trinomial I have left over. So let's see here. 5 and 3, I need negative 5 plus 3 in order to get negative 15 when they multiply, and negative 2 when I add them together. So that means that I have zeros at 0, 5, and negative 3. And remember, I get those by setting each of these equal to 0. Okay? So I'm going to plot those on my graph over here. So I've got 0. I'm going to say that this is negative 3 right here, and this is 5. I'll go ahead and write 0. Okay? All right, now to get a sketch, I need to, well, before I do that, sorry. Notice these all have a multiplicity of 1, okay? So these are just going to cross through the x-axis. And then based off of this, I have a positive leading coefficient, and I have an odd degree for my end behavior. It's 3. So the positive leading coefficient of 1 means the right side will point up, and an odd degree means that the left side will point in the opposite direction. So when I go to connect my zeros, that's what my end behavior should look like. And remember, since they all have a multiplicity of 1, I am just simply going to cross through the x-axis with these. Don't need to worry about bounces or making slides or wiggles. And that's it. All right, number 2. It says let f of x equal that equation right there, and write an equation for f of x in factored form and determine the values of x where f of x has a whole or a vertical asymptote. All right, so we're going to factor and simplify down here. So f of x equals, factoring this is a difference of 2 squares, so x plus 4, x minus 4, over, this is a trinomial, so x and x, factors of 28, the add or subtract to get 3 would be 7 and 4. And I want a positive 7 minus 4 in order for that to factor correctly. And notice that my common factor is x minus 4, so those go away. And I'm left with x plus 4 over x plus 7. Okay? All right, from there, I want to find the whole. So I know that the x value of the whole will be 4. Now to find the y value, I'm going to plug 4 into the simplified function. So y would equal 4 plus 4 over 4 plus 7, which is 8 over 11. So my coordinate point is 4, 8 over 11. Okay? And then my vertical asymptote is, remember, in the denominator, set the denominator equal to 0, so x would equal negative 7. Okay, so this is so far just kind of like a review of everything. All right. Oh, wrong way. Sorry, still trying to get used to making videos again. There we go. Given the rational function r of x at the right, analyze and graph. So first it wants us to write an equivalent form by factoring. So let's factor that out. So r of x equals, let's see, that will be x and x, 4 and 3, both positive. And then my denominator will be x and x. Let's see, 3 and 2, positive 3 minus 2. That looks good to me. And my common factor is x minus 3, or I'm sorry, x plus 3, my bad. So I end up with x plus 4 over x minus 2. All right, now it says find any zeros. So the zeros are, remember we find them in the numerator of after you take out the whole. So once I take out the whole, then you find the zeros. So that would be at x equals negative 4. Find any values of x where r of x has a whole. So that is just as the value of x. You don't actually have to find the whole. So it's going to be at x equals negative 3, since the common factor was x plus 3. Find any vertical asymptotes. So the vertical asymptotes is what's left in the denominator. So x minus 2 equal to 0 means we get x equals 2. And then find any horizontal asymptotes. Notice that the degree of both the numerator and denominator are 2, and because that those are equal, I'm going to divide my leading coefficients. So 1 divided by 1 equals 1. So y equals 1. All right, and then I need to graph this, and then I'm going to find the domain. Okay, I think it's easier to sketch and then find the domain. So let's start plugging these in. So I have a 0 at negative 4. I have a whole at negative 3, but I don't know the y coordinate. So to find the y coordinate, I'm going to plug negative 3 into my simplified function for x. So negative 3 plus 4 over negative 3 minus 2. And I get, let's see here, 1 over negative 5. So that occurs at negative 3, negative 1/5. So let's see, negative 3, negative 1/5, it's going to be like right there. I have a vertical asymptote at x equals 2, so let's plot that. Make sure your asymptotes are dashed or dotted, whatever you want to say that those are. And your horizontal asymptote at 1, y equals 1. Okay. All right, from there it looks like this graph will kind of go down like this, but let's double check. I'm going to find the y-intercept because that will give me enough points right there. So to find the y-intercept, I'm going to plug zeros in for x right here. So I end up with 12. Those are zeros over negative 6. 12 divided by negative 6 is negative 2. So 0, negative 2 is a point. And that looks like it gives me enough data to connect my points and get an idea of what this graph will do. Clearly this graph goes, it decreases without bound up to here. So now I'm going to pick a few x values over here to see what happens on the right side of the vertical asymptote. It could decrease without bound, or it could increase without bound around the vertical asymptote. To double check that, you want to pick actual x values and plug them back into the equation. So I'm going to use x equals 3 and plug it in right here for x. And when I do that, just to save time, that's going to equal 7. So 3, 7. You would plug in 3 for, excuse me, all the x values, okay? And then at 4, that one would be, let's see here, 16. Whoops. Sorry. It's a little more than 4. It's like 4.4-ish. So you guys can start to see these points kind of go down. I'm going to also do 5. which is 3. All right, so you guys can start to get a good idea of what that does right there. All right, so then now that we have a sketch of our graph, we can find the domain and range. So, or just the domain, that's all it asks for, sorry. So this starts at negative infinity. And as I work my way to the right, I have discontinuity at x equals negative 3. So I gotta stop at negative 3. Then I start back up at negative 3 again. And I go all the way to 2. I get stopped at 2, and I pick up again at 2, and this goes towards positive infinity. Now remember, we used parentheses on infinity signs. The reason why I used parentheses on the negative 3 is because it's a point of discontinuity. The function does not exist there. And same thing at 2. That's another part where the graph is discontinuous. Okay? All right. Flip it over. Okay, number 4. It says the graph of a rational function f of x is shown at the right. Write an equation in factored form for f of x and explain how you know. So, all right, let me make this so I can write a little better. There we go. All right, so let's see here. I have, I'm just going to write out some like key features that I have to help me. So I have a hole at x equals 4. And because I have a hole at x equals 4, that means that I'm going to have a common factor in the numerator and denominator. So, to explain how you know, that's what I'm kind of doing right now, kind of working backwards in a way. So, common factor in numerator and denominator. Okay? And then let's see, I have a vertical asymptote at x equals 2. So I will have the factor x minus 2 in the denominator. I have a 0 at x equals negative 3. So I would have the factor x plus 3 in the numerator. And you would actually want to write out denominator and numerator on a test or quiz. Just doing this shorthand for notes right now. And then, let's see. I think that's pretty much it for right now. So if I have f of x, because that's what it says the graph is, I'm going to go ahead and write that information in. So, the common factor in the numerator and denominator, by the way, would be x minus 4. I probably should have wrote that. So I get x minus 4 in the numerator, x minus 4 in the denominator. I have x minus 2 in the denominator, and I have x plus 3 in the numerator. Okay? Now, we can kind of check ourselves here to make sure that this all makes sense. Notice if I were to FOIL these out, I get x squared and x squared. And when I have x squared and x squared, those both have a degree of 2. So I would have to divide the leading coefficients. So 1 divided by 1 is 1. And that's where I have a horizontal asymptote. So that actually all checks out right there. Also, if you were to plug in zeros, let's see, that would give us negative 12 over positive 8. Yeah, so negative 12 over 8 is negative 1.5. And if you guys look at this, it's that y-intercept is about negative 1.5. Okay. Also, if you would want, you could plug in 4 right here for x, because if we pretend that we cancel those out, 4 plus 3 is 7. 4 minus 2 is 2, so 7 over 2 is, let's see, 3.5. And if you guys look right here, the hole is about at 3.5. So that's the function. That's all we need there. Okay? So that all checks out. All right, now let's put this all together and dig a little deeper. So in the last lesson, we found a hole in the graph would occur when a common factor cancels out, and the rational expression was simplified. Let's explore what happens when the common factors have varying degrees either in the numerator or denominator. What is the outcome? Will this be a whole or vertical asymptote? Can you make a prediction? So we've actually already talked about this, so this part should be a review. So consider the two functions below. Write an equation in factored form and find any values of x where the graph of the function would have a whole, a vertical asymptote, or a horizontal asymptote. All right, here we go. So I'm going to factor this out here. I'm going to take out GCF of x in the numerator, so I get x squared plus 2. And in the denominator, that's already in factored form. There's nothing else we can do there. And I can't do anything else on my numerator. So we can go ahead and start discussing. Oh wait, actually, sorry, my bad. These x's, this is x to the first, this is x squared. So that leaves me with x squared plus 2 in the numerator. And I only end up with 1x in the denominator. Okay? So that's what we got there. All right, now I can find all that information. So I have an x in the denominator, which means I have a vertical asymptote at 0. At x equals 0. And that's when the factors are larger in the denominator. Remember, if the power is larger in the denominator, or the factor is, compared to the numerator, then you have a vertical asymptote. Okay, let's see here. I will not have a whole because I didn't have any common factors there besides the x, but we took care of that with a vertical asymptote. I also have a vertical asymptote at x minus 3. Oh, I'm sorry, at x equals 3, my fault. So yeah, that's what x would equal there. So there's one there as well. And then I do have a horizontal asymptote here. And the reason why I have a horizontal asymptote, let's see here. The numerator is a degree of 3. The denominator is actually a degree of 3 as well, because this is to the power of 1. And if I multiply that, that gives me x to the third. So I end up with x to the third over x to the third. And when that happens, remember you divide the leading coefficients. So 1 divided by 1 is 1. So I have a horizontal asymptote at y equals 1. Okay? All right, letter B. Let's see here. So, you know what? I'm going to circle this in case we didn't see it. There we go. All right. Letter B right here. So this is already in factored form, as you can tell. I can reduce this as x plus 3 in the numerator over x minus 2. And then I end up with x plus 1 in the denominator. That's all I have left over after, because this is a degree of 2, and that's that's an exponent or a power of 2, and this is exponent or a power of 1. So, I have a vertical asymptote at x equals negative 1. I have a whole at x equals negative 3. Because that factor canceled and I had leftovers in the numerator there. So that happens when the factors are larger in the numerator. And then I have a 0 this function has a 0 or a root or an x-intercept at x equals 2. Because remember, those are, you find those in the numerator when you set the numerator equal to 0. Okay? Alrighty. All right, so can you make a conclusion about the behavior of common factors and the degrees of the factors related to their position in the rational functions compared to the numerator and denominator? So if I have equal factors, then I have a whole. If the factors are larger in the numerator, I have a whole still. And if the factors are larger in the denominator, you have a vertical asymptote, which we have discussed this stuff multiple times. So hopefully we got it down by now.